Hello. Good morning to you. Welcome. Hello, Chef. Welcome. Good morning, Uchu. Good morning, Top Wolf. Welcome. Hello, Pig. It's been, I think it's been 12 days since you've seen me last. Is the microphone still working? You guys can hear me? I don't sound terrible. Hello, Yang. Okay, thank you. Alright, I'm going to open up everything on my computer now and try to break the stream real quick before class starts. Alright, that went well. Go over here, and we're probably down here somewhere. Good morning, YCS. Good morning, Cade. Okay. Alrighty then. Let's see here. First thing we're gonna do today is we're gonna talk about something. Let's see. I think we're here. We'll talk about that. We are going to talk about assignment 8. The first thing I want to do, though, is I just want to make a point clear. I just want to make a point very clear to you guys. If you are exceptionally keen to understanding recursion, this assignment may take you 10 minutes. Do not use that as an excuse to start late, though. You might have to think very hard to get your solution. I saw the Discord blow up last night. Okay? So I just letting you know, I warned you guys, alright? This stuff is pretty hard. And yeah, your solutions, I don't know, some of you might have done a lot more than what I did, but your solutions might have been just 20 lines of code. 20 lines of code. And so I do know a lot of people, I'm not singling anybody out here, a ton of people had a lot of trouble just like figuring out what was wrong with their program. Kind of in a helpless state, just like, here's a picture of my code. I don't know what's going on here. And even though it's recursion, there's still a lot of things in this that you know. You should know that these are, some of the variables are passed by reference. Some of the variables are passed by value. All right, you know that. You know that the functions have return types. So in the first program, the island counting one, that one returns an integer. So likely, you can store the result of that function in an integer. You can also return a call to that function. But in the second assignment, that recursive function was void. And the void, you can't return a void type. All right, you just kind of call that one. So you don't really store the result of that one anywhere. And so all I'm saying is that even though the concept of recursion is hard, I do think that we should have an understanding of how to draw out our functions and see how they work. All right? I talk about reading your code like a book a lot. Oftentimes I do that. If you message me with a problem you have, I'll just look at your code and I'll kind of read through it step by step and I'll say, what happens here? What happens here? So my hope is on Thursday, because today is the late deadline, I'm going to allow you to finish up those recursion assignments if you want. But on Thursday, I think we're going to go through one of them, and I'm going to have a purposely broken code. Actually, a very common one that I saw many of you use, in which you were editing the original parameters, the current string and the car. Yeah, so if you're doing the late deadline, my hint to you is do not edit the original parameters, current string and cars left. You definitely want to use temporary variables for those. But we will use a piece of broken code, and I'll get out maybe Excel or Microsoft Paint, and I will draw those function calls out for you one by one, just to give you an idea of what that looks like. So when we get to this next assignment, linked lists, which I assure you, you guys are going to have a great time with. My hope is that you can kind of be able to debug a little bit of these functions yourself. All right? So I hope you think that's fair. Of course, you're welcome to come to office hours, and I will help you kind of I'll help you kind of learn to debug some of these things yourself. So if you want to do that, you're welcome to. Yeah, so Giovanni says, I feel like the approach of identifying the base case, the reduction and the reduction operator helps you understand the recursion a bit better. And that's absolutely correct. The very first thing you want to do with recursive functions is identify the smallest amount of work that you can do in one function call. All right, so in the islands one, the smallest amount of work you can do is identify one piece of land. And then you can just recurse in all the directions. And so that's it's very simple. I mean, I'm not trying to rub it in anybody's face. I'm just saying when it clicks for you, it makes a lot of sense. Similarly with your permutations assignment, the smallest amount of work that can be done is you add just one character to the current string. You say, all right, I've got this character left. I'm going to put it in the string and recurse. And you say, what's the base case? Well, I have no characters left to add. So yeah, I do appreciate that. And I would recommend that when it comes to recursion, you need to identify those things first. What's the smallest amount of work that I can do at one time? Fuzzy and Mail, great time or great time? I would say the latter. I mean, you might have some furrowed eyebrows, but we're approaching the end of the semester here, and we're just going to have to get good at these things. So we'll see. I'll give you plenty of time to do it. Chef says, the function call in the for loop is where I get lost. Like if I call a recursive function in the loop, when does the loop iterate? Well, we can talk about that. I was sending you guys this picture. It didn't have much context. I was showing you the recursion trees 2 weeks ago, right? In which we would draw them out on Microsoft Paint. And so I was actually sending you guys a recursion tree. I sent it in the main Discord. And I guess understanding it was not perfect, which is fine. Let's just take a look at it. I gotta pull it over here real quick. All right. So, here's the recursion tree that I sent you. All right. Now, what I was trying to get across to you is kind of how this function works. So I have them kind of color coded on levels. And so this is the very first function call that happens up here. So here the current string is empty, right? I said the current string is in the box. So the current string is empty, and you have all of the characters that you want to put in the permutation. Okay? And so you notice that this function calls itself 3 times. Now, so Chef says, when does the iteration continue? Well, so you're going to start out here. You have a for loop, right? You're going to do something like for I is less than the size of characters left. Your first call will be here at I equals 0. Now, I'm sorry for my terrible mouse writing, but this is I equals 0. So it's going to recurse over here, and then this one does its for loop, right? And it calls this one. This is a different I equals 0. Whoop. Wow. I really got to work on that, don't I? So this is also an I equals 0 here in the for loop. And then this one calls itself again, right? Comes down here. This is I equals 0 again. Terrible. Just terrible. And then down here, you're in the base case. So you're in the base case at this point. So this doesn't do any recursion, so it cuts off. And it returns up here. And then it returns back up here, because there's no more for loop to be done here either. There's no more for loop to be done here. But now we do have some for loop left, right? We did I equals 0, so now we go here to I equals 1. Right, and then you come down here, and now we're at a different for loop. This is I equals 0. And then base case, you return back up. You return back up. And then this one's for loop is done, so then you finally come back up here, and then you finally move on to I equals 1. So, terrible handwriting there. I don't know if that makes sense. Would you guys let me know if it does? This top for loop doesn't continue iterating until this whole left subtree finishes. All right? So you just kind of have to think of bigger picture here, all right? This whole big tree over here, I mean, it's a huge tree, and it kind of executes from left to right. So the very first for loop, when I equals 0, it does this whole tree first. And then you come up here, I equals 1, it does this whole tree. And then finally, I equals 2, it does this whole tree. Right. So if you think about it, right, this function calls itself here, and then it calls itself, and then it calls itself, oh, I'm done. Comes back up, calls itself again, calls itself, I'm done, comes back up, calls itself, calls itself. It's like what we call is depth first search. So you'll learn about that later. But it goes as deep as it can go from left to right. So it will say deep, 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 deep. This is as deep as I can go. Now I'll come back up. I still have some depth here to go, so I'll go here. Now I'll come back up, and now I'm back up here. I'm ready to go as deep as I can. Come back up, go as deep as I can, come back up, and then similarly here. That's how it works. All right, so if you think about it, by the time you get to this function call over here, so by the time you're done with this whole tree, and you're just right here, in fact, as soon as you call this, you're already going to have ABC in the permutation list and ACB. They'll already be in there. Hopefully because you pushed these to the vector in the base case. Okay. So that's that. Uchu asked, how many more assignments do you have? You have 2 assignments. And the last one I'll give you until I think the Saturday of that finals week. I think grades will be due that following Tuesday or something. So I'm going to give you a ton of time to do that one. I'll let you determine that for yourself, Mail. Okay. So one more thing I wanted to say. Obviously, I overlooked something in this assignment, and that is, depending on how you did this assignment, you may have these kind of things flip-flopped. Meaning you might have started from I equals 2 and worked your way back. And if you did, that means this tree would be over here, and this tree would be over here. And if so, your ordering will be different. You're going to get CAB, CBA, and then the B's, and then the A's. And so obviously the code grade's not matching. All right, I did recommend you could sort them. And for all of the tests on code grade, that works, except for the XBB case. All right, so if you fail that one, just look at the test. And as long as it says the 3 permutations that are there, XBB, BXB, and BBX, you'll get full points, okay? I'll manually review that. Are there any more questions that you want to talk about this recursion thing? I will kind of just show you the other one. It's not as pretty as this tree, but I'll give you a little introduction to that. And also, I want to mention, I do think I had one submission for the, well, I had 2 submissions, but one was a little bit cheating. But I do think I had one submission for the non-recursive version. So I will be checking that, hopefully. And I might be able to show it in class next time, which would be cool. From the look of it, it looks very complicated, and that was the point of doing this assignment recursively. You're over the assignment. All right. That's fine. No more assignment. No more assignment, you say. That's totally cool. So, looking at this tree, by the way, I guess I'll pull it up. This tree is a very interesting tree. Just to think about it, this tree is a very interesting tree. And the reason is because you notice that it kind of looks like a 3 area to start, right? You've got 3 branches here, but then it goes down to 2, and then it goes down to 1. And so, in fact, based off of the number of characters you have that you're generating in your permutation, you're actually going, that's kind of how big the tree is. It'll start out, if you have 5 characters, it will start out 5 wide, then it goes down to 4, 3, 2, 1, just like a factorial. On the other hand, the other program, let's take a look here. This one is a straight up 4 tree. It's a straight up 4 area tree, in which this here might be your, can't make it bigger, but this one here would be your main function call, right? You just pick some random point. You identify that that is a space on the map. It's some land. So you get, hey, I've got +1 land here. And then you say, I'm going to check up, I'm going to check down, I'm going to check right, and I'm going to check left. So you definitely just want to draw out these trees if you can. If you're getting help from me, you obviously note that I was sending these pictures to you. So with that being said and done, let us move into class today. What do you say? Today will be a fun day. And we're going to have to think pretty hard today. Now, you've learned recursion, so this could be a very easy subject. But this might be the kind of last hard thing we've got going on in this class, and that is linked lists. All right. So it looks like today I'm going to be doing the dash lines. So we're going to call this the linked list day, or we refer to them as LLs, because typing words is hard. This is what we're working on today. So I know you guys love dynamic arrays. Obviously, the template assignment was your favorite. So let me just show you another way to do a dynamic array. And that's through linked lists. 2 L's, that's not the way to think about it. So let's kind of take a step back and think about our dynamic arrays that are stored in pointers. All right? So let's just take a one-dimensional dynamic array. So one-dimensional dynamic array stored using a pointer. All right, so we've done this plenty of times, right? What do you do there? That's when you say something like int array is equal to new int, say 5. Okay, so that's what that looks like. That's a dynamic array because then we can delete this memory and get some new memory if we want. Now, the things to note about this is obviously what I've been hammering into your head this whole time, that this is contiguous in memory. Contiguous, I think I spelled that right. This is contiguous in memory, meaning side by side, meaning the elements are side by side. All right. Now, there are some kind of pros and cons to that. All right, let's think of some pros. Does anyone want to take a guess at what a pro of this is? And maybe a con? I'll take any. Pros and cons of this. Can you identify anything that, you know, this might be a pro or might be a con of having something like that? So Pig says easy to access. That's absolutely right. A very easy and fast access. Very easy and fast access. That's absolutely correct. Very easy and fast access on those. Now, Cade says adjustable size. That's true. Now, I'll say that both linked lists and dynamic arrays have adjustable sizes. So we'll kind of push that to the side for now. And Pig says, what if memory is full? And Uchu says you can find memory without... I think that might be correct. But let's talk a little bit about what Pig says here. He says, what if memory is full? Well, I'm going to kind of boil this down just a little bit to say that all of the memory needs to be side by side. Contiguous. It's a requirement. And so if you have a very large array, right? Say you have in a 1,000,000 element array. You better hope that RAM has 1,000,000 contiguous spots. Hopefully. Right? Hopefully your RAM has 1,000,000 spots all side by side. Okay. Yang, you are correct. Absolutely, you can get the next element very easily. That's what I'm saying here. Very easy and fast access. Why is that? You just add an offset to the address and you dereference it. Right? That's what the brackets do. So that's why that's a huge pro of that. And it's fast. The con of it is all of the memory needs to be contiguous. So say you got 1,000,000 elements. You need a spot in RAM of 1,000,000 side-by-side elements. Now that's not always going to happen. As we talked about before, I showed you in that Excel sheet, pretty much the reason why when we resize an array from a pointer, we have to delete the old memory and request new memory. And that's because what if there's no kind of extra memory left off to the side of this array, right? If in this array we've got 5 extra spots or just 5 spots, and then we say, hey, we want to add an extra element in here, well, you better hope that this spot over here is not being used. Now, that's usually never the case. This spot over here is almost always being used by your brother's Minecraft program or something like that. So, this is why we have to allocate. We have to request more memory. Say, please give me 6 spots, but they also have to be side by side. And then I've got to copy everything over, and it's just a great time, right? You guys love all of that inserting, push back, push front, and deleting. I'm sure you guys had a great time with that. So that's pretty much it. Do we have any questions about this? On the pros and cons? Pros and cons of this? This is pretty much it. All right, that's pretty much it. I wouldn't say there's anything more that we need to consider for a dynamic array that's being stored in pointer. So now we're going to talk about a linked list, okay? We're going to talk about a linked list. So I'm just going to add a little bit of a header here to indicate that this is our traditional dynamic array. Now we're going to try out the linked list, the LL, the LLL. All right, so the very first thing, what do you think is different about a linked list compared to a dynamic array? Take a guess. Obviously, I've been talking about some of this stuff already, so you might be able to get it right. What do you think is different in a linked list compared to a 1D dynamic array stored using a pointer? It's not contiguous, yes. Linked lists are not contiguous. That's exactly right. All right, they are not contiguous. Now, I'm going to say let's do some pros and some cons for this. But I'm also going to ask you this question because I want you to think about this a little bit. With a linked list, we need a spot for the element, all right? So let's kind of just jump into here a little bit what linked lists look like. We're going to say that elements are stored in nodes. And nodes consist of two things. And I want you to take a guess at what those are. What's the first thing that the node consists of? And there's something extra. You can think of, say, these as being nodes up here, right? So they're going to store, obviously, the value or the element, right? That's very good. The first thing they store is the actual element. Now, the next thing they need, you guys are saying address, memory location. Can you tell me the address of what? That's my question to you. The address of what? Absolutely, absolutely there's a pointer there. And yes, that's absolutely right. It's the address to the next element. That's absolutely right. Nice job. Yes. And that's what makes a linked list. All right. So linked lists are not contiguous. All elements are stored in what we call nodes. And nodes consist of two things. One, they have the actual element that's being stored there, an integer, a string, whatever it might be. Maybe it's a template type even, your favorite. And then it contains the address of the next element. That is, how am I going to get to my next element? I'm going to follow this address there. Are the components of a node contiguous? Yes, they are. Yes, they are. In fact, we're going to use Excel today. I'm going to kind of show you this in Excel. So let's go ahead and get that little whiteboard going right now. Yang says it is one element and one pointer. Yes. Now, there might be two pointers. There might be two pointers. And we'll get into that in just a little bit. All right. There's a few different types of linked lists. Okay. So you're going to learn a little something about structs today. All right. Here we are in Excel. A little something about structs and classes. Now, this is roughly correct. All right. You're going to have, say, a struct node. All right, and now let's pretend that this node has a few things. Perhaps it's got its int. We're going to call it data or data. I don't care what you think it is. I call it data. And you're going to have a pointer to the next node. So what does that mean? It's a little bit recursive. A node struct contains a pointer to a node struct. It's a little interesting to think about. All right. Whoops. Let's go ahead and open that up. We'll put that there. So that's kind of what our node looks like. Chef says, because your element could be a pointer. Yeah, you could do that. Now, this is always going to be an address to the next node. This will never contain an array. But this, you could have, kind of back to that bonus test question, right? You could have a list of nodes pointing to lists of floats. Yeah, this data could be an array if you wanted to. This could be whatever you want. But this has to be a pointer to the type of the struct. So if it's struct node, this is going to be a pointer to a node. If this is struct Jimmy Neutron, this is going to be a pointer to Jimmy Neutron. Now, if we're going to do ints here, we have to consider the size of this. Are we... Okay. We're going to consider the size of this. So this is going to be 4 bytes. And this pointer, well, let's take a look. I never know this off the top of my head, so let me just break the computer real quick by pulling up... I'll pull up Edge, Microsoft Edge. Hopefully we won't freeze. Obviously, we're getting close here to noon, so knock on wood. Let's not jinx it. All right, let's see here. All right, so depending on your computer, the address, if it's 64-bit or if it's 32-bit, it'll either be 4 bytes or 8 bytes. All right, I'm working with a 64-bit computer, so we're going to say, hey, this is probably 8 bytes. So this pointer is worth 8 bytes. This int is worth 4 bytes. So what does that look like in memory? Well, let's take a look. Let's go ahead and shrink these down. Column width, I don't know. Let's do 3. That looks nice, doesn't it? We'll kind of get rid of that. So how do we need? We need 1, 2, 3, 4 bytes for the integer, and then we need 1, 2, 3, 4, 5, 6, 7, 8. 8 bytes for the address. All right, so this is what your node looks like in memory. I think Pig asked this question, so I hope that this answers it. Your nodes are contiguous in memory. Here you're going to have 1, 1, 1, 1 or something. I'm not going to put those in there. So your integer is stored here, and your node pointer is stored here. All right, but notice that this is quite small. All right, this is only 12 bytes of data. So the only requirement that your RAM has to have is, do you have a bunch of little bits of 12 bytes? A bunch of little 12 segment bytes. All right. And so this probably, there's another one probably over here. I'll put it maybe right there. And in some sense, you're going to have a pointer to this, right? So this one might point here to the starting location of that one. And then you might have one over here. And this one might point to that one. And so you'll see a nice little picture today when I get to it, because we're going to talk about the different types of linked lists. But that's kind of roughly what your linked list might look like. Are there any questions on that? Okay, I'm just going to make these a little bit smaller. I don't know what I said, maybe 3. Yeah, if you do have 2, you can point them to each other. You'll learn about what we call that in a little bit, unless you want to take a guess. What might you call something like that, where the front points to the tail? The front points to the end of it. What might that be called? Looped, I like it. It's close. We call it something else, though. We call it something else. All right. All right, so let's do our pros and cons list real quick. Circular, that's what we'll call it. Yeah, circular. Sorry about that. Yeah, that's what it is. That's what it is. The Spider-Man meme. Quite literally, they're pointing at each other. That's amazing. Yeah, we call them circular. You'll see. So we're gonna do a few pros. Obviously, the first pro is that. Memory does not have to be contiguous. All right. In addition to this, can anyone think of some advantages of this? Can anyone think of an additional advantage over something like this that a linked list might have? And it spawns from the idea that the memory is not contiguous. Why did I type loop? Obviously, a con of this is that accessing elements is a lot slower. In addition to that, you need more memory per node. Per element, I guess. So, I guess, Fuzzy, I just proved you wrong there. You do need more memory per element. In a dynamic array, you need only 4 bytes per element, and they're all going to be side by side. But now we're doing a linked list, so we actually need an additional 8 bytes to store the pointer. So you do need more, you do need more memory per element. Right, so Chef says you're likely to have a bunch of little bits than one big free side of the memory. Yeah, that's correct. So I'll give this one to you. Guess what? Inserting and deleting is much easier. So think back to your template assignment. When we're doing push back, push front, insert, or delete, whenever you do one of those things, what do you have to do? You have to go to the operating system and say, I need a whole new array. And then I have to do a for loop and copy it all in there. And then I've got to delete the old array. And then I've got to put the new array into the old array. Right? Just a ton of fun stuff, right? Guess what? With the linked list, you say, I want to add one element. Well, you just request a node from memory and you can link it right in. You don't have to resize or anything like that. You just request a new node and you link it in. Or you can delete a node out and you can link the 2 nodes that was pointing to it and that it's pointing to. And it's easy as that. Having flashbacks? Well, prepare to have more flashbacks. All right, so linked lists, obviously, just like your template assignment, will have some pros and some cons, right? Just link a new node in. Yeah, Synthos, that's absolutely correct. Right? You guys, I think there was a lot of confusion on that last time, right? With the dynamic memory. Why can't we just shove another one in there? Well, because the memory is contiguous. Now that the memory is no longer contiguous, we can just add a new node. We don't have to do all that jargon that I just said. Does it make sense? You can just link a new node in or out. Hey, operating system, I need 12 bytes for a new node. Thank you. I'll just put it here in my linked list. Easy as that. Easy as that. So those are pros and cons. All right, those are pros and cons. Now we're going to talk about the types of linked lists. Harder to understand equals better for program. Yeah, a little bit. You're not wrong. You're not wrong. All right, so there's really 2 kinds of linked lists, okay? Kinds of linked lists with some variations. All right, now we're not going to talk about the variations yet. Let's just talk about our 2 kinds of linked lists. Now we have a singly linked list. All right, now this is what we just talked about, all right? All nodes point to the next node. All right. Now, what's the other one? What's the other one you think we might have? Any guesses on this one? What's the other one we might have here? Okay, multi-linked. I do like it, yeah. We will refer to them as doubly because we're just going to have 2. Now, one node will point to the next node. Where do you think the other pointer in the node points to? So in a doubly linked list, we're going to have actually a few things. So let's go ahead and get these out here just so you can see them. We're going to have a struct node. How about SLL node? All right, and in here you're going to have your type data, and you're going to have your node next, right? The previous node, absolutely, Chef, that's right. So in a doubly linked list, nodes point to the next node and to the previous node. So let's kind of bring this out here just so we can see it. So this is what we're going to call it an SLL here. This one we're going to call a DLL. All right. Nodes here point to the next node and previous node. All right, so pretty much you just have to copy this one, bring it over here. Now we're going to call this a DLL node, and this one has a node next, and it has a node previous. Yes, Fuzzy, you're right. You're absolutely right. You're absolutely right. So an SLL here, if you think about it, if we're going to do a DLL, we're going to need 1, 2, 3, 4, 5, 6, 7, 8. 8 more nodes again. And this one will be for the previous node. So you've got node next here. And here you've got node previous. So you're absolutely right. Ha! I love it. That is great, Giovanni. That's wonderful. Yes, absolutely. What is the difference? What is the pro and the con of the SLL versus DLL? SLL versus DLL. Well, you guessed it, with an SLL, you can only traverse one direction. A DLL can go both ways. All right. So this kind of, it'll bite you in the butt on a few things, right? Swapping nodes, perhaps. You know, getting the previous node. Something like that. It can bite you in the butt a little bit. So you need to weigh the pros and cons of doing something like this. All right. Obviously, with an SLL, you have less memory to use, but perhaps slower access of elements. And things like swapping, sorting, inserting, all these things are a little more complicated because you have to kind of keep track of what the previous node is. So they're a little more difficult because of you can only traverse in one direction. Make sense? Now with a DLL, in addition to this, before we go, you always need a head node. All right, I'm going to show you this in Excel in just a moment. With a singly linked list, there always needs to be, you always need to keep track of which node is the head. Otherwise, you can't get back to it. All right, so I'll talk about that in just a little bit. We're going to illustrate it so that you can see it. It'll make more sense to you. Now, obviously, with a DLL, you need more memory. But everything up above becomes so much more simpler. Pig, I'm a little confused on what you mean by traverse. And that's fine. We'll get into that in a little bit. Just to kind of give you an idea, let's say I need to access the third element in my linked list. I kind of have to hop around the addresses. Does that make sense? Does that make sense? So, like I said, I'll show you in just a moment. But if this is our head node up here, and I want the third element, I have to go, here's my head. I'm going to take a look at this address. I'm going to traverse over here. I'm going to look at this element, and then I'm going to traverse over here. And here I have, I don't know what's stored in here, 111.0.0.0, 1, don't look at those. Something like that. You go, oh, here's my integer. Does it kind of make sense? Oh, no. Guys, please tell me when you're back. Okay, thank you. Yeah, please, we'll wait a second. I just realized that our timing is all off because of daylight savings time. Daylight savings time. Right? So we're going to have to look out. What was that? Someone mark it down. It's 12:12, right? It's 12:12. And we'll prepare for it next time. All right, guys. Thanks for that. Hopefully our only hiccup for today. Let's get back into our notes real quick. All right, obviously, DLL, you need more memory, but accessing elements might be the same, but if you're going the other direction, I guess I'm going to kind of combine these two notes up here. I'm going to say accessing too. Accessing, swapping, sorting, inserting, all this stuff is a little more difficult because you can only traverse in one direction. You're kind of limited in that regard. But all of the things above, what we call cons, above in the SLL become easier. Because we can traverse both ways. Hey, I need my previous node. I'll just check my pointer, you know. If I'm going to swap two nodes, I need to look at my previous node. I'll just follow my link there. It's pretty easy, all right? So all the other cons above, right, these are kind of the two cons. Accessing, swapping, sorting, all this stuff. I'll make this a little wider. Are all more difficult because of the traversal method. In this case, all of the other cons above in the SLL become easier because we can traverse in both directions. All right, so we're pretty close to XL here. We're just going to introduce a few more things. Now we're going to get to the circular part. All right, variations of linked lists. Now, this one's very binary in that it can be non-circular or circular. A non-circular and a circular. So we kind of guessed it before. In a non-circular, well, in a circular, let's start with that one instead. The tail element, that's what we'll call it. The tail element, and I'll define those for you in a moment, points to the head element. Okay, let's kind of define those real quick. What's your head? The head is the first element in the list. And what's the tail? The tail is the last element in the list. Now I'll ask you, can the head also be the tail? Is that possible? Can the head also be the tail? Yes, it can. Absolutely. The first element in the list could also be the last element in the list. So, in a circular linked list, the tail element always points to the head element. And if it's a doubly linked list, if DLL, the head points to the tail as well. Okay? In a non-circular linked list, the tail points to null pointer. Okay? And if you're doing a DLL, the head previous points to null pointer. I'm going to use this kind of arrow thing because we're going to do that a lot. All right? Because we're working with pointers, so we're going to get back into using arrows again. All right? The head previous points to null pointer. Makes sense? So those are variations. So what does that mean? Well, you can have 4 linked lists all over, all together, 4 linked lists total. You've got a NC, a non-circular SLL. You've got a circular SLL. You've got a non-circular DLL. And you've got a circular DLL. Circular. Okay. Make sense? And that's it, all right? So why don't we take a moment before we start typing more notes? We can save some of them for next time. Let's make some pretty Excel diagrams. What do you say? All right. So we're going to save that sheet for later, and instead we'll kind of come up here. I'm going to start small just because. We'll make it maybe this big. That should be good. Oh, should we do dark mode today? Top Wolf says, so both of them cannot be randomly searched, right? Yeah, it's not. That's kind of a hard question. All right. Are you talking about like generating a random index and going to that element? Because you could. You just have to traverse that way. Maybe I can answer this question with some diagram here. So let's make a few blocks of memory. Okay. All right, here's our memory. All right. So now let's make a linked list. Let's go ahead and pull up VS Code while we're at it. And I just kind of want to put some code in front of you. We're not going to code too much, but I do want to make the structs available to you. So I do have a CPP file already. So let's go ahead and get that going. All right, so if we're going to do our DLL and our SLL, let's go ahead and just kind of mark those. Here we've got our SLL and we've got our DLL. All right, so if we want to do that, we use structs for these. We usually don't use classes. Why is that? Well, if you think back to the rule of thumb, we're not including any member functions with these nodes. You could if you wanted to. I won't stop you. But in general, we're just going to directly access the data and the pointer. So we're going to store them in a struct and not a class. So we'll call it an SLL node. In general, you'll just name it node. Perhaps we'll do snode because that's a little bit easier to type. All right, so that's for our singly linked list. So you're going to have some data in here. Perhaps we want to make it a template, your favorite. Type name T. And you're going to have your type data here. And you're going to have a snode pointer to the next one. All right, and that's it. That's your node. Now we're going to do the DLL. I just like to copy this. We'll make this a D node. You're going to have your type data, and you're going to have a D node to the next, and you're going to have a D node to the previous. Now, guys, I just had an epiphany, a realization. I don't know if you remember, but when we were first talking about pointers, I told you that I preferred to do it this way, where the pointer is next to the variable name, and not like that. And I said when I got to it, I would let you know why I like to do that, and I've just discovered why. Notice here that if we're going to do two pointers side by side, you have to put the asterisk on each of them. This won't work. This is very stupid. What is this? This is a pointer to a node and a node. Isn't that terrible? This one here is a pointer to a node, and this one is an actual node. Similarly, if you did this, int pointer 1, pointer 2, one of these is an int pointer, and the other one is an int. To me, that doesn't make sense at all. I mean, in my opinion, this is a type, and I would prefer that this carried all the way this way. But if it makes sense to you, that's fine. But this one is a pointer, and this one's an object. So I like to put it here. I like to put it on the variable name. That's why I like to do that. Fun fact. Okay, so those are our nodes. All right, and they're templated up. And you can pretty much copy those verbatim if you want. So now, let's go ahead and just make some nodes in Excel, shall we? So let's say we want to make a linked list of a few elements. And let's just start with some. I want to make this maybe white. Maybe I can make it just a lot bigger here, something like that. So let's do a linked list of some elements. All right. Let's make this this list here 2, 3, 4, 5, 6 in memory. So this is probably going to look like this. First thing we're going to do is request a node. First, we'll start with the SLL. All right, so you're going to have a node somewhere. Now, remember, you're going to request it from the operating system, so it's going to pop out of nowhere. All right, let's kind of make these different color. We're going to have a yellow, and perhaps we're going to have a, I don't like that, maybe an orange. We'll give it a nice thick border, too. So that's going to be our node. All right, this is going to be our node here. And it's probably stored at some address here, 0x00a. And in here, you're going to have your element 2, right? That's at the data. And then here, you're going to have some other address, 0x0012 or something. Okay? So this is our first node. And so what this person, or not this person, but this node does is it points somewhere else in memory. So say we're going to want to insert. Let's insert 3 to this linked list. Well, we're just going to request some memory from the operating system. Let's make it thick too. Can we do that, please? All right, go that way. Okay. And what is this? Well, I'll just copy this briefly. Nope. There we go. And we said that this address is 0x0012. What's stored here? Well, we're going to put 3 here. And then this one, right now, let's say points to null pointer. All right, so notice up here is the head of the list. This is what we'll call that. This is the head. Make that bold, and we'll even make it big. That's the head of our linked list. And right now, this is our tail. And how do we know it's the tail? Well, this is just a non-circular SLL. And so we're going to have that point to null pointer. So this is going to be non-circular. Now we're going to insert 4. Well, very similarly, we're just going to say, hey, please give me some new memory from inside the RAM somewhere. I don't care what address I get. Perhaps it's 0xccab. We're going to put 4 there. And then we have to link it in the list. So what do? We say, hey, this pointer here is equal to this memory location. So that becomes 0xccab. All right. It's making sense so far, right? And so let's just quickly insert our last few elements. Now, we could get some elements that are contiguous, right? We could just request some more memory, and here's going to say, you know what? You get what's 12 plus 12 bytes of memory. It's going to be 4. I don't know. We'll figure it out here. Let's do some addition. 12 plus 12. You're going to get 4 on one side there, and you're going to get 2. Perhaps it's 24. But no. It's too hard for me. Let's just pretend like this is 0x0024 or something. All right. That'll be our 5. And that is now going to point there. So that's going to be 0x0024. And this goes here. So it's making sense, right? I really don't have to spend too much time here talking about this. This is what it looks like. And finally, we could have something down here. There you go. There you go. 5 and 6. That's our linked list. Fuzzy says, I'm assuming if you wanted to insert something in the middle of the linked list, it would be as easy as just inserting at the end, right? No, that's not correct. And why is that? Well, my face here is in the way. How terrible of me. How terrible. So it's kind of not. All right, because when you're inserting an element at the end of the list or at the head of the list, you really don't have to rearrange anything. You can just kind of pop it on the end, or you can pop it up front. If you're going to put it in the middle, you're going to have to say update this. You're going to have to update the node that was pointing to. So we're going to do an illustration of this later on, so I won't try to confuse you too much. So let's kind of just start with this. You'll see inserting in a little bit, and it is not as easy as putting it at the end or at the front. So are you okay with this? This will go up on Web Campus, this little picture here. And now we're going to make a few extra ones, all right? I'm going to show you all of them and what they all look like. Lessons, today we're doing linked lists. This will be our SLL, our NC SLL, okay? Now our next one is, let's say I want it to be circular. Well, that is pretty easy. All I have to do is add an arrow here. Now I want this arrow to be kind of curvy because it's not going to look very good. So I am going to kind of do it like that. There you go. And we'll come over here, and it comes back all the way up here. Okay. And there you have your circular linked list. So there's not much of a change there. I guess that's 0x00a. Okay. It's not much of a huge change there. It's just that the tail element will point to the head element. And now I really need to get smaller here. So that is our circular SLL. Hopefully no problems there. Now I'm going to ask you a quick question here. And hopefully you can see the problem, or say a pro and a con of a circular SLL and a non-circular SLL. So let's say we have a head pointer somewhere. See, here it is. We're going to put it, I don't know, there. Now that head pointer is always supposed to be pointing at the head of the list. Now in a circular linked list, it might not matter too much, but in a non-circular linked list, it might matter a little bit. So let's assume that the head is pointing here. Now via traversal, and what do I mean when I talk about traversing? I mean I follow these arrows around until I get to the element that I want to get to. Let's say that this is the first element over here. But the head of our list is pointing here for some reason. Can I still get to this first element by traversing the list? Can I still get to this element by traversing the list? And when I traverse, I'll be starting from the head. Absolutely, right? I follow this arrow to here, to here, to here, to here, and bam, I'm at the first element, right? Now, what if I take this away? Can I get there? Obviously, no. Right? Obviously, no. As soon as we make this a non-circular, if the head is pointing anywhere in the list beside the first element, you have memory leaks. How do you get here? How do you access this element? How do you access this element? Well, you can't. You have no pointer that's saved to the location of these things. Okay? We actually lost two elements. We lost this one and this one, right? We can't get to this one either because the head is pointing here. That's a memory leak. So Synthos asked, the head doesn't need to be the first element. Well, I always say that it does, all right? I always say that it does. Now I'm just going to ask you, this is kind of a fun test question. Of the 4 types of LLs, which one absolutely requires a node to be pointing at the head. I kind of already answered that one for you, right? It is obviously a non-circular non-circular SLL. All right. Now, Synthos, traditionally, the head will always point to the first element in the list. And there will almost never be a reason to do that, like to not follow that rule. You're probably always going to have a head node. But the thing is, when you traverse it, it can be quite dangerous in that you're going to want to make a copy node. Now, we're going to get into the coding on Thursday, all right? So don't have to worry about it too much right now. But when you're traversing the list, you don't ever want to change the head node, because the moment you change it, you're going to lose these elements. The moment that you update this head node to look somewhere else, you've made memory leaks. So I hope that's helpful to you. Usually the head will always be looking here, all right? It will always be looking here. But if there's any case that it's more important than other cases, it is absolutely in the case that you have a non-circular SLL. Because in fact, with a DLL, let's get to that. Let's do a non-circular DLL. This one's very, very simple. Now we're just going to kind of pad on some things here. Right? We're just going to pad on some colors. That goes there. Now I am going to shift this over. We're going to put that there. We're going to put that there. I guess I want this to be this light blue color. Oops. There we go. And we'll put this one here. So each node immediately becomes a little bit bigger, right? And each of these will contain some amount or some address, right? No, so let's start with these one at a time. This is the first element. This is a non-circular DLL. Where is this previous node pointing to? What do you guys think? Where's that previous node pointing to? If it is a non-circular DLL. Didn't I put this in here? Maybe I did, maybe I didn't. Where's my arrow? I don't know. Any ideas? I told you already. It's in the notes there. Null pointer, right? This is not pointing anywhere. Similarly, this last one down here is also pointing nowhere. Well, actually, no, it's not. The next node here is pointing to null pointer. Right? Now we're going to go ahead and add in some arrows. I do want them to be different colors, so I am going to put that one there. Now this previous node, you'll kind of see here, it's going to get a little ugly, so I'm just going to add these little double arrows here side by side so that you can see them. And I do want this to be, like I said, some other color, maybe green. Might be a little bit hard to see. How about yellow? It's not so bad, but it's still kind of bad. So in the case of the DLL, this one is going to be pointing back up here. So this contains 0x0a, 0x00a. And then you come over here. Now, obviously, this one here is going to be pointing back down here. Right, so this previous node is going to contain that address, 0x0012. Similarly here, this node down here will be pointing back up at this one. What's that address? 0xccab. And then finally down here, this one will be pointing back up to this one. It's pretty simple to visualize. Obviously, this is kind of kindergarten stuff. When you get to coding it, it will not feel like kindergarten stuff. But when you're looking at it in nice, pretty pictures, it is. Okay. So this is a non-circular DLL. Right? Notice that nothing is pointing back and forth. Here you can see that, nothing's pointing back to the first element. And nothing's pointing to the tail, aside from, I guess, that element. But it's non-circular. That's the point. And you'll notice up here that the head element, this first one, it's null pointer on the previous. All right, it's null pointer on the previous here. And if you look down here at this tail element, this one is null pointer on the next node, right? Now, I ask you the same question again. Notice that we're still in a non-circular DLL. If I'm pointing back here, the head is, can I still get to this first element? It's a bit of a trivial question, but what's the answer to that? Can I still get there? Absolutely we can, right? Because we're here, now we'll just take the previous traversal back, and then we'll take this previous over here, and we're at the head. So that's the point I'm trying to make, and this is a test question I like to ask. Of the 4 types of linked lists, which one is absolutely required a node to be pointing at the head? All right, and it's just the non-circular SLL. The non-circular SLL is the most dangerous when it comes to traversing. And when I say dangerous, I mean you're gonna be kind of stepping on I don't know what the term is. You kind of want to tiptoe around because you're working with memory, and you can lose it very easily. All right, you can lose it very easily. So this will be our non-circular DLL. Oop. I'm going to save that image. And finally, we'll just kind of add some arrows in here for a circular DLL. This one's just very simple, right? We're just going to add 2 arrows. This is going to be our NC DLL. And finally, we're going to add these 2 here. Control C, V. This is the next node. We've got ketchup and mustard going on here, as you can tell. So that's going to kind of point back up there. I don't want them to intersect. So that points back there. We can kind of put it here. Give me the small one here. All right, does it make sense? Everyone's happy? All right, the tail next points back to 0x0a, or 0a, and then this previous one points down to 0xccc. And there you have it, folks. That is our circular DLL. And those are our 4 types of linked lists. And that's really all we have to talk about for today. I'll kind of review those. I'll make sure, or just double check to make sure we've got all of our notes. And then we'll pretty much wrap it up here. So let's take a look. Fuzzy says, can we have a linked list point to another linked list? Yep, absolutely. That's 100% possible. You are more than welcome to do that. You just have to link them. That's all you have to do. You just have to link them. That's it. So let's check our notes here. We talked about pretty much all of the important stuff. Now let's just make a quick note here. When traversing any linked list, you always want to declare a new node pointer variable as your traversal node. Why? This will help us avoid changing head or tail pointers. All right. So that's what I was talking about up above. In that, you know, if you absolutely wanted to, in any DLL or in a circular SLL, you could change the head node and make your way back there. That's fine. But even then, you really don't want to do that. So when it comes to coding this stuff, you're going to code some things. You're going to code a bracket operator. You're going to code an insert. You're going to code a delete. All of this stuff is going to require you to traverse through the list. And if you're going to do that, you're going to want to declare another node. I call it traversal, usually. And this traversal node will point to things on its own. So you say, look at the head element. All right, now I need to go to the next one. Now I'm looking here. Now I need to go to the next one. Now I'm here. Let's go to the next one. Now I'm here. Let's go to the next one. Now I'm here. And let's go to the next one. Now I'm back here. So notice the traversal node will be updated all the time, but our head node will remain constant, at least through that process there, all right? So that's kind of a note. So whenever you're coding something, the very first thing you should think about is, do I need a traversal node? And if I do, declare it and use it, all right? It'll make more sense when you see it in code, all right? So that's pretty much it for today. If you have any questions, please, now is the time to ask, all right? It's a pretty light day in terms of coding. We didn't do very much of that at all. Tons of notes, obviously, and some pictures. Chef says, is it common to pass the address of a head node as a parameter of a function? Absolutely it is. Absolutely. That is 100% correct. Now, the way we're going to learn to code linked lists, we're going to actually put them in classes. All right, we're going to put them in classes. So what we're going to probably have is we're going to have, say, some template. We're going to have a linked list class. And in this class, you're going to have some stuff like this. So you're probably going to have, we're going to make this a template, obviously, because we're templating stuff up now. And you're going to have, say, a node of some type, pointer head node. And you might have an int size. And you might even have a tail node as well. Now, in here, you're probably going to have some things like, I don't know, you might have a deallocate list. But if we wrap this up in a nice class, you don't have to pass it as a parameter because it's here. So if you're kind of freeballing it in main, yeah, you will pass that head node as a parameter. But if you wrap it up in a class, you won't need to because you'll have access to it up here. I hope that answers your question. If it doesn't, you can let me know. I don't mind. But just to give you kind of an idea, this is what we'll be doing next time. We're going to wrap it in a class so that we don't have to pass addresses around as parameters. Just because doing that from main, it's just a little freaky. Freeballing a linked list in main is never really any fun. We're definitely going to want to use some objects for that. Notice here we've got some composition going on here, right? We've got a struct inside of a class. We've got some composition going on there. So, hang on to your seats. Next time, we're going to hop into this code, and you're going to see what fun linked lists can be. And then on Thursday, we'll also maybe have a chance to talk about drawing out function calls and stuff like that. So, that's all I got for you today. Thanks for coming to class. Just sleep on this stuff. Come back on Thursday ready to learn. I hope you guys have a wonderful rest of your day. And Wednesday, I'll have office hours in 15 minutes if you want to stop by. If you didn't finish the recursion assignment, you can still turn it in late, all right? So come say hi if you want to. And that's all I got for you. So, yep. Uchu, you are welcome. I'm glad that you learned a lot. Synthos, you are welcome. Cade, you are welcome. You have a good one. Pig, you're welcome. Chef, you have a great day yourself. Giovanni, you are welcome. Top Wolf, you're welcome. Fuzzy, I appreciate that. I'm glad we could put some pictures in front of you guys. Have a great day, and I will hydrate right now. And YCS, you are welcome. Have a great day, guys.